y'all are good.
So before we start today, I'm going to need everybody to stow your calculators, return your desk to its upright position, and prepare to take off into the world of calculus. Okay, so as you probably guessed, our presentation is on airplanes. I am your pilot, Gavin Fuchs. This is my co-pilot,
Holland Weilinga.
Okay. So we chose airplanes because number one, I'm super afraid of airplanes. I hate flying. I think going up 30,000 feet in the air in a 400-ton piece of metal is kind of testing your fate, and she, on the other hand, loves flying. But on a more serious note, calculus is said to be the math of change, so what's more fitting than an airplane in which you tilt the steering wheel or change a rotor by mere degrees, and the result is huge changes in altitude or course in general.
Okay, so some of our goals that we're going to touch on this presentation is we're going to write a position function for the altitude of the flight, and this is with respect to time. And we're going to analyze the takeoff to see what happens during a normal takeoff. And we're going to analyze the landing to see what happens during a normal landing. Okay, so the first thing we did was we actually found a flight log from Minneapolis to Miami, and the plane that was used was a Boeing 747. And so this flight was on May 19th, 2019. It took off at 5:32 and landed at 8:47. So the flight was 195 minutes. So looking at the flight log, we actually took altitudes every 5 minutes, and these are the points that we plotted on the graph to create our position function. So this position function is with respect to time. So the input would be time, and the output would be the height or the altitude in feet. And so from this graph, we decided that the best thing would be to create a piecewise function because there's 5 main parts of the graph. So that is how we split it up. So the first part of the graph is takeoff. So we plotted the points from 0 to 25 minutes, and we use a quartic regression model with an R-squared value of 0.9950. And just a reminder that the closer the R-squared value is to 1, the more accurate the model is. So this is why we chose the models with the largest R-squared value. And we determined this equation to be right there. So the second section of the graph was from 30 minutes until 130 minutes, and since this was the main part of the flight, it was pretty flat because the altitude stayed at a pretty level height. So the best R-squared value we calculated was only 0.3436, so we determined that the best way to describe this section of the graph was to use a constant. So we just took the average of the altitudes between these times, and it was 32,004.7619. Alright, the third section was the first tiny descent, so it's from 130 minutes to 140 minutes, and this could be from different reasons, but it's most likely due to another plane passing nearby or some turbulence. And so we use a quadratic regression model with an R-squared value of 1, and this is what we determined the equation to be. The fourth section, we plotted the points from 140 minutes to 170 minutes, and we also used a quartic regression model with an R-squared value of 0.9848, and that is what we determined that equation to be. But all of the altitudes were around 28,000 feet for this part. The fifth section is the landing. So we plotted the points between 170 minutes and 195 minutes, and we use a quartic regression model with an R-squared value of 0.9987. So this is the final steep part of the flight, and that is what we determined the position equation to be. So from this, we came up with a piecewise function, and that is listed right there with each of its intervals. But for the purpose of this presentation, we're just going to focus on the takeoff and the landing because that is where most change is going on. In the other parts of the flight, it's mainly constant.
So the first thing we did in our analysis of the takeoff was take the derivative of our position function, which as you guys know is the velocity function. From this, we were able to find the area under that curve, which gave us the total distance of 32,253.285 feet. So that was the total distance that took the plane to take off. And then dividing that value by our interval, we were able to find the average velocity to be 1,290.1949 feet per minute. Further, we took the second derivative of the position function, or the first derivative of that velocity function, to get the acceleration function. After doing this, we were able to perform the first and second derivative test. So here's our first derivative test. As you can see, the velocity function actually does not have a 0 on the interval 0 to 25 and is positive for that whole interval. So altitude is increasing for all that interval, which would make sense as we are taking off. Here's our second derivative test. Here, the acceleration function had 1, 0 at 22.7349. So on this first interval, the function is negative. On this second interval, it's positive. So this kind of indicates that velocity was actually decreasing for most of the ascent until the very end when the plane got close to cruising altitude. It started to increase again. And that kind of came as a surprise for us because we thought the velocity would be kind of increasing or constant for the majority of the takeoff. And then just after that, we put a few points into our velocity function just to make sure everything checked out and to kind of back up our first derivative results. So as you can see, like I mentioned in the last slide, the velocity was decreasing for most of the, or was decreasing for most of the takeoff. So the plane started off really fast while leaving the runway and then slowly decrease until getting close to cruising altitude, and if this would keep going on, it would start to increase again. So that did back up our first and second derivative results. We did pretty much the same thing with the landing, so we started again by taking the derivative of our position function to get the velocity function. We integrated that to get the total distance under the curve to be 18,560.834 feet. So again, that is the total distance that the plane took to land. That was less than we thought it would be. And then in dividing that by our interval, we were able to calculate the average velocity to be negative 319.8656 feet. So as you can see, this value is negative. So because our position function is altitude or like upward movement with respect to time, a negative velocity value would mean downward movement and a positive would mean upward movement. So having a negative average velocity makes a lot of sense considering we are descending. And then again, we took the second derivative of the position function to find the acceleration function, and then performed the first and second derivative tests again. So the velocity function has zeros at 172.531, 185.307, and 192.675. On that first interval, it's positive, the second interval negative, the first interval positive again, and then the third interval negative, fourth interval negative, sorry about that. So that means that everywhere it's positive, or altitude is increasing, everywhere it's negative, altitude is decreasing. So this again kind of surprised us. We didn't think the plane would actually, or once it started its like descent, we didn't think it would be rising again. However, as you can see, it was. And then the acceleration function for the second derivative test had zeros at 177 and 189.389. And then that one was negative on the first interval, positive on the second interval, and negative on the third interval. So after this, we looked at a few things and drew some conclusions, which are on the next slide. So first of all, we determined that altitude was increasing from 170 to 172.5319, from 185 to 192. So again, like I kind of mentioned, that came as a sort of surprise to us because we thought once the plane started descending, it never would increase again, but it did because that's where the velocity function is positive. And then on the flip side of that, altitude was decreasing on those other intervals where that function was negative. And then finally, one of our basic conclusions was we looked at where the first and second derivative tests were both positive or negative to see where speed was increasing, and we determined that speed was increasing from 172.5319 to 177.6201, from 185.3072 to 189.3894, and from 192.6757 to 195. Again, since those were the velocity acceleration functions, were both the same one. And then just as with the takeoff, we put a few points into our functions to kind of back up our results. So the places in green are where the values are positive, and the places that are red are where values are negative. So as you can see, speed is increasing here, and here, and then here. Which again backed up our results.
Alright, and here are just the sources we use.